Okay, welcome everybody to our Monday afternoon seminar. Today it's a great pleasure to have with us Eva Mueller from Portsmouth and Oxford, who will tell us about SDSS, the 20 years of cosmological results. So Eva, please, you have the floor.
Yeah, all right. So thank you very much for having me. And let me just jump right in if I can change slides. Yeah, okay. So my talk today, I'm going to first give an overview over the Sloan survey, in particular, and the part that I was working on, the eBOSS survey, the extended baryon acoustic oscillation spectroscopic survey. Give a short introduction of what are baryon acoustic oscillation, these BAOs, and then show some results from the DR16 release of eBOSS. That is the final cosmological release of SDSS, and show some cosmological constraints on our standard model, in particular focusing on dark energy. And then I will go a bit into the Hubble constant tension and what we can learn from BAO, and also particular what we can learn from eBOSS. And then in the second half of my talk, I'm going to focus on how can we use large-scale structure, in particular eBOSS data, to constrain primordial non-Gaussianities. All right, so what is eBOSS? As I said, it's a baryon oscillation spectroscopic survey, and it's part of SDSS, so part of the Sloan survey, using Sloan telescope in New Mexico in the US. And here you can see a fly through 20 years of SDSS data, starting with the early SDSS galaxies from 2000 to 2008. And then continuing with the BOSS galaxies, so the baryon oscillation spectroscopic survey, the luminous red galaxies, as well as then continuing to higher redshifts for the eBOSS survey. Now here you can see the emission line galaxies going to further redshifts than the LRGs. And also we have the clustering of quasars. On the one hand, we're using directly the clustering of the quasars, but also the Lyman alpha forest. So this is a nice overview, and you can see how the large-scale structure of our universe, so the large-scale structure that you also can see this fluctuation in the CMB, how they're imprinted in the clustering of galaxies. And now with eBOSS, we can really trace our universe from redshift of 0 up to a redshift of 3, 3.5 using the Lyman alpha forest. Now here again is an overview over the different surveys, including the young blue galaxies, the ELGs, the old red galaxies, the LRGs, for both for BOSS and for eBOSS, and the early nearby galaxies, measuring the nearby galaxies and the low redshifts. Now, the way the data was being taken was we had these SDSS plates. So these were aluminum plates where you had holes drilled into them for each one of the objects that you wanted to target. And then you had these cartridges that you pushed under the telescope several times per night to get the redshifts of your galaxies and quasars. So eBOSS really is a spectroscopic survey, not like DS, for example, the dark energy survey that only has photometric redshifts. So meaning we have really, really precise redshifts. And here you can see a video of presumably a poor undergrad students who had to pluck these optical fibers by hand for each of these plates. Now, luckily, with the upgrade of BOSS, the dark energy spectroscopic instrument, DESI, these will all be automated, and we don't have to burn through a lot of undergraduate helpers to get our data. Nowadays, most of these plates you can probably see for outreach, and you can here see various uses as lamps or also as doors for these SDSS plates. So for those that do a lot of outreach, I think you can still get some of these plates if you want to use them in your outreach projects. Now here's an overview over the eBOSS and BOSS footprint, again, where we have this 3 or 4 different tracers in the clustering of galaxies and quasars, the low redshift BOSS LRGs, the high redshift eBOSS LRGs, and then also the eBOSS ELGs and the quasars, the QSO, covering several thousand square degrees of our sky in the NGC and the SGG. And here you can see some more details of the different surveys. You kind of have different targeting strategies. So with the quasars, the idea is to cover a really, really wide redshift range, but then of course the quasars have a low densities. The ELGs have intermediate redshifts and very, very high number densities. And the LRGs, slightly lower number densities than the ELGs and at lower redshifts as well. On the right-hand side, you can see the Lyman alpha forest really going to the extreme high redshift up to 3.5. All right, so now what are these baryon acoustic oscillations? Well, first of all, the way we use this baryon acoustic oscillations is really reusing them as a standard ruler. And you might have heard from Supernova that you can use Supernova as standard candles. Here the idea is the same, that we have this intrinsic quantity in the clustering of our galaxies, this BAO scale, that we can use and measure throughout the history of our universe. And since we know the intrinsic length, we can from that interfere the expansion history of our universe. In the same way, we can use the light of the type 1a supernova as standard candles. In that sense, we are very lucky that nature throws us this observable that we can really use. And as I said earlier, this large-scale structure that we are observing within the clustering of galaxies really are the same fluctuations that you can see in the cosmic microwave background in the CMB. And for his work on the large-scale structure, J.S. Peebles recently shared the Nobel Prize. All right, so where are these BAOs coming from? Well, it's coming from a phase in the very early universe where you had a Higgs plasma and the baryons and the photons were coupled. And here you can see in a simulation by Daniel Eisenstein, where you can see that it's acoustic because it's a pressure wave, so it's a sound wave pushing outwards, and oscillation because gravity acts as the restoring force, overall giving us then this imprint of the sound horizon at decoupling or at the drag epoch. So this is now, in the previous slide I showed you for just one overdensities, but of course you have these overdensities all over the sky. But you can see how this ring is really imprinted all over the clustering of our galaxies. All right, so what are we actually measuring? So what are we measuring? Really 2 things. We are measuring angle on the sky, and we are measuring delta in redshift, so a difference in redshifts. And what we can measuring by that is, on the one hand, we have the angular diameter distance, and on the radial direction, we get a measurement of h of c, so the expansion rate of our universe, so the Hubble expansion. Now, this factor of RD will become more important later on. So keep that in mind, that we are not directly just measuring h of c and dm of c, but we have a factor here of the sound horizon in our measurement. So how do we do our measurement? Well, we're using 2-point statistics, and that basically means we are counting galaxy pairs. So we're looking for galaxy overdensities on the sky, and we're doing this by simulating a random catalog and then compare our measurements to that. Once we have this overdensity usually on a 3D grid, then we can either do the calculation for Fourier space, so looking at the power spectrum, or in configuration space, directly looking at the correlation function. And now for those in cosmology and also in astronomy, you probably have seen this many times before. In the end of the day, what is being done with the BAO is measuring this bump here at roughly 150 megaparsecs. So you can see this is the 2-point statistics, so the correlation function. Without the baryons, you would just get this power law decay. And with the baryons, you get this baryon acoustic oscillation feature in here that we are trying to measure. All right, now from SDSS, now we get really a total BAO distance ladder all the way from redshift of 0.15 with the main galaxy sample, all the way up to redshift over 2 with the Lyman alpha forest. And what's plotted here is the BAO measurement in relation to the Planck best fit model. And now here also you can see the different traces again, the BOSS LRGs, the eBOSS LRGs, the eBOSS ELGs, the quasars, and the Lyman alpha forest. And you can see that we get really nice agreement with Planck for all of our measurements. Now, the BAO is not the only thing we can measure. There's also something called the Retrospace distortions. That basically means you have the peculiar velocities of your galaxies that distorts your measurement in redshift space. So anything that is like a circular overdensity will appear squashed in redshift space, just because galaxies further away or in falling appear that they're closer to us. And here the close galaxy appears like it's further away from us overall, giving the squashed feature. Now, this retrospace distortions allow us to measure the growth of structure and with that constrain modified gravity. But I just wanted to mention it for the remainder of the talk. I will mostly focus on the BAO and then later on also on the primordial non-Gaussianity. But here you can equivalently see a measurement for the growth rate. So this is F sigma 8 in relation to what you would get from Planck. And also you can see here that we find good agreement with the Planck CMB measurements. Yeah, a couple of more useful links for the press release from last year, and also more overview for the eBOSS program if you want to use it in your lectures or outreach. All right, so now we have these measurements of BAO and RSD, but what we really want to know about what does this tell us about dark energy? Now, this is the paper from last year where we had a really broad overview of all the different constraints on our cosmological model, where I was corresponding author. So I was in charge on getting all of these ellipses and constraints that you will see soon. All right, so here are the measurements, how they were before eBOSS. In the first panel, again, you see dm, dh, which is basically 1/h, and also the luminosity distance. Here for in red, you can see with a non-zero curvature, with a dark energy equation of state that is not exactly -1, and you can also see with the sum of the neutrino masses. So here were all the measurements before eBOSS, and you can see here now with the eBOSS measurements, you can really see how you fill the gap of the intermediate redshifts with the BAO, in particular with the quasars, but also with the ELGs and the higher redshifts LRGs. Now, this redshift coverage, again, really allows us a very precise measurement of all of these different cosmological models, just because we have this broad redshift coverage. Now, here is a plot from the Supernova Cosmology project, and this is how cosmology looked more than 10 years ago. And here's now an updated version with eBOSS, where you can see that with all three major cosmological probes, the CMB, the supernova, and also the baryon acoustic oscillation, all three independently gave a detection of dark energy, so a non-zero omega lambda here for several sigmas. So here, and also for the remainder of the talk, the CMB TNP is Planck temperature and polarization. Supernova is the Pantheon sample, and BAO is the full set of SDSS BAO measurements. Now, what's plotted here is an open and free curvature lambda CDM universe. And here the black dashed line is for omega k of 0, so for a flat universe. All right, so far so good. Everything I told you so far, things look consistent. But if you look a little bit more into the details, then you will see that there are a couple of issues. One of the sometimes called crisis in cosmology is the so-called Hubble tension. So Hubble tension here really just a measurement of the expansion rate of our universe that by now is well known. However, the question really is how fast is the universe expanding? Because we have two main discrepancies here between the CMB, the Planck measurement gives us a very low H0 value, so 68. And the cosmic distance ladder, the SDSS measurement, gives us a very high measurement of the Hubble parameter. So much so that by now this tension has risen to more than 5 sigma. Now, these two measurements are very different with regards to many things, but generally speaking, the distance ladder is more low redshift local measurements, where you also really need to calibrate your supernovas. And you're doing that by having this ladder build up from going from the geometry to the Cepheids, and then using the Cepheids to calibrate the supernova. So the supernova without this calibration is doesn't give you this absolute H0 value. It just gives you the distance modulus, and you can use it to constrain dark energy, but you can't get an absolute H0 value. Now, the CMB, on the other hand, is coming from very different redshifts, so very early redshifts. And also the assumption underlying here is that we follow a lambda CDM cosmology that then allows you to infer from this very early measurement your H0 value, so your Hubble expansion at redshift of 0. All right, so what can we learn from BAO? So BAO by itself can really not give you a concrete H0 value. But let me just go you through this slightly busy plot. So on the left hand, what is plotted is the value of H0, with the gray band here is the measurement from the distance ladder. And on the axis you have the sound horizon. And remember earlier when I said, well, we're measuring angles on the sky and differences in redshifts, that gives us really only a ratio between the Hubble parameter and the sound horizon. So we have this perfect degeneracy from BAO by itself. However, we do get good measurements on the overall meta density of our universe. And this is plotted here on the right-hand side. Now, we can break these degeneracies in multiple ways. So one way is to use information from Big Bang nucleosynthesis. In particular, this gives us a prior on the baryon density. And now, because the sound horizon depends on the overall all matter density and the baryon density, you get the constraint on the overall matter from the BAO, and if you add in, you can break these degeneracies with the baryon densities, which then gives you an H0 value. And what you can see here, this measurement that is fairly independent from the CMB measurement gives you also an H0 that is around 67, 68, and is in tension with the distance ladder measurement. Then what we did next is we wanted to do an inverse distance ladder. So a ladder, because we really use the CMB, the BAO, and the supernova, going from the very high redshift to low redshift. And on the same time, we wanted to have this analysis as much independent of dark energy and the overall background. So we assumed a very general model here where free curvature and the two dark energy equation of state parameters are also varied freely. But even in that case, that gives you the magenta uncertainty. You can see, because we have now 3 extra parameters compared to lambda CDM, the constraints get a bit wider, the error bars larger on H0, but you can also see the dark energy can't really explain the difference between the CMB and the distance ladder measurement of H0. But you can also think of it, instead of an H0 tension, you can think of it as an actual tension in the sound horizon. So the purple contours now is if you use the BAO measurements plus the distance ladder H0 measurement. And then you can break these degeneracy here. And you can see then, instead of talking about a H0 discrepancy, you can talk about a RD tension. So it's just a different way of phrasing the same problem, really. All right, and I should also mention that the Lyman alpha forest measurement here is really, really crucial for this H0 constraint, because the degeneracy direction changes as a function of redshift. So combining really the low redshift BAO and the high redshift BAO measurement allows you to get a really, really tight constraint on H0 compared to if only using the low redshift BAO from eBOSS. All right, and here you can see an overview of how much eBOSS has improved the overall constraint on our cosmological model. So here we have a couple of additional parameters. So we allow the dark energy to vary, as well as curvature, the sum of the neutrino masses, and the dark energy of quasar state. So compared to a standard lambda CDM model, we have 3 additional parameters. And you can see on the one hand, how much consistency there actually is between stage 2. So this was the DR7, so the year 7 BAO measurement, the GLA for the supernova and WMAP. Then adding in SDSS-II, that data set. Stage 3 then is with DES, the dark energy survey, Planck, and also the Pantheon sample. And you can see on the one hand, really good consistency, finding with a flat lambda CDM model. So meaning a dark energy equation of state that is good in agreement with -1 and curvature of being 0. So now this was a broad overview over the cosmological constraints from eBOSS. There were in total more than 25 publications. There was a big round of publications last year. And also many people in the IFT were working on it with Violetta and Santi and others. For now, we have obtained over 4 million spectra. And it's more spectra actually than the rest of the world combined. And this really concludes the stage 3 for spectroscopic surveys. Indeed, with eBOSS finishing, the cosmology part of SDSS is finished. even though there are other non-cosmology surveys going on within SDSS. Right, so now this was all focusing more on standard cosmology, but what I wanted to talk now in the second half of my talk is a paper that I published last summer. This is how we can use the eBOSS sample to constrain theories in inflation and to constrain primordial non-Gaussianities. So the idea is here that with the large-scale structure, you can measure more than just BAO and RSD. In particular, you can measure primordial non-Gaussianity within the large-scale structure. So this is a very neat way in which you can actually observe the very early universe. But signatures in the very late universe. So really what we're trying to do here is by measuring primordial non-Gaussianities, we can distinguish between different models of inflation, with inflation being this very rapid expansion in the very early universe. Now here's simulations where you can see effect of primordial non-Gaussianity. So FNL is the parameter that just give you an estimate over the amount of non-Gaussianity. So it's the more non-zero FNL is, the stronger the non-Gaussianity in your sample. And you can see here how primordial non-Gaussianity increases the overdensities and decreases the underdensities. Now, so far, the best constraints on primordial non-Gaussianity are from Planck, with being in agreement with 0 and with an error bar of ±5. But all the future improvement from that will come from galaxies surveys, in particular from DESI, the dark energy spectroscopic instrument, but also Euclid, W1st, and other surveys. Now, how are we doing this? Well, by measuring the galaxy bias, in particular on large scale. So what do I mean by bias? Bias is just the ratio between the clustering of galaxies compared to the clustering of dark matter. And what was found more than 10 years ago is that primordial non-Gaussianity actually gives you a mode coupling between the short and the long wavelengths, which then in Fourier space means you get an overall 1/k² behavior on the largest scales, meaning that the simple galaxy bias usually is independent of scale. But on top of that, we get an additional contribution that is proportional to the FNL parameter, but with a 1/k² dependency. What that means now is if we measure the galaxy power spectrum, we're trying to measure here the very largest scales, so the small k. And you can see, again, here the effect for different FNLs. The solid line is for 0 FNL, and the dashed line gives you the 1/k² scale-dependent effect. So now in that way, by constraining the bias on very large scales, we're constraining the amount of primordial non-Gaussianities, and any detection of non-zero primordial non-Gaussianity would, for example, rule out single field inflation, so the standard inflation. So this is kind of the thought process, how we can use the late universe to constrain the very early universe. And,
sorry, Eva, can I ask a question?
Yeah.
So in this case, do you have to assume some ansatz for the bias, or can you get like model independent constraints? Do you understand what I mean?
So usually when we do this kind of analysis, you marginalize over the linear bias.
Okay.
And in that sense, you do make a couple of assumptions, in particular that it is linear on the very large scales.
Okay.
But other than that, we're not, in my analysis, I don't really have to assume a specific number for the bias, if that's what you mean.
Yeah, okay, thanks.
All right, and now here are the results. So I did a study analyzing the eBOSS quasar sample. And what you can see is I'm finding also an FNL that is in agreement with 0. So -12 plus -21. And these are actually the tightest constraints on primordial non-Gaussianity from galaxy large scale structure. So you can also see it's not as tight yet as the Planck constraints, but we're getting there. What actually took the longest in this analysis is studying the systematic effects at large scales. And here you can see the study that I published last July came with a companion paper, where the companion paper really focused on using machine learning to constrain the systematic effects in order to get a really good measurements of the primordial non-Gaussianities. Now here also, if you compare the red with the black, it is a technique using optimal redshift weights and without using optimal redshift weights, and I will explain that in a second. Now here is, you can see, here's the actual measurement of the eBOSS quasar sample, where in the top you have the NGC and in the lower part we have the SGC with the best fit in orange. And you can see that we find fairly well agreement with this FNL of 0 measurement. Now, I should say that if you look more into the details in the scale-dependent, bias in FNL, what you will find here is actually you have another additional parameter P in there in the equation, which goes back to the merger rate of your tracer. So usually in previous studies that was assumed to be 1, which is for the ELGs or LRGs, seems to be a good fit based on simulations. But that really assumes no recent mergers, and for the quasar sample, that is really not a good assumption. However, in theory or in principle, this parameter isn't very known, and you can see is that actually they're very, it changes our error bars quite a bit. So it does not shift the maximum likelihood value, so we're still getting a best fit FNL of around 0. But you can see that if we make these assumptions about the merger rate, then we get plus minus 14. So since it is not 100% known, I would say that our error bar in the optimistic case, plus minus 14, in the more conservative assumptions, plus minus 21. That is kind of the current range on error bars on primordial non-Gaussianity that you can get from large-scale structure. All right, so now what are these redshift weights that I was talking about? Well, I think it's a very simple and neat way you can improve your constraints from large-scale structure, and you can use it for primordial non-Gaussianity, but you don't really have to. It applies to any kind of other survey that you want to constrain. So the basic idea here is that usually we apply so-called FKP weights, that is just statistic-based weights trying to balance out shot noise and cosmic variance. So in the end, you always upweight your high redshift galaxies because you have fewer galaxies at higher redshift. But on the other hand, if you, for example, have a physical theory that really kicks in at low redshift, then this might actually not be the best strategy. So here the redshift weights are basically a combination of taking the underlying theory that you want to measure into consideration, and then kind of finding a sweet spot between the purely statistic weights that you're applying and the physical theory. Now, in the case of FNL, actually, it goes the other way around. So it's more, the effect is larger on high redshift. So what you actually want is upweight the high redshift galaxies even further, more than you would just with a simple FKP weights. All right, so this was suggested by a previous study, and the general idea from simulations was that we would expect roughly a 30% improvement on the FNL constraints overall, depending a bit on the redshift range. And that is exactly what we were finding with the actual data. So I was very pleased to see, you know, when you first write a paper that's purely theory-based and then you apply it to the data, that you actually get exactly out what you would expect. So kind of a bit on the, depending on the assumptions, but the optical weights give you an improvement up to 30 to 40%. And now here you can see in blue, this is the redshift distributions without any optimal weights. And then in orange and in green, you can see if you apply the optimal weights, again, for the two different merger rates. And you can see is that overall, what I said earlier, you are increasing the overall effective redshifts to higher redshift. So instead of an effective redshift of 1.5, the quasars then have an effective redshift of 1.8, 1.75. All right, now the second important thing I wanted to mention is, as I said earlier, the longest part in all of this analysis was really trying to figure out the observational systematics. So the problem really is that the largest scales, the small K range really is affected the most from any kind of systematics, just because there are just not that many modes. So your purely statistical signal to noise is bad. Now here in orange, you can see the linear treatment that was used for the standard baryon RSD analysis. And you can see that both in the NGC and the SDG that we found really an excess of clustering on these very large scales. But we didn't believe that it was really cosmological because of various tests. So we started working on this neural network approach. And you can see how much of a difference this new neural network treatment for the systematics. So you can see how important this new treatment is. And in green, you can see the mean of the MOX power spectrum. So what do I really mean by systematics and by systematic treatments? Well, different samples are affected by different things, but in particular for the quasar sample, what has a large effect is the number of stars that are in your field, also the extinction and the depth here plotted in the G band. So here what is plotted is really the number of galaxies compared to the number of randoms for different bins of a specific systematic. And what you can see is that without accounting or without correcting for the systematics, you really get a trend with these different systematics. So what's usually being done is just a linear treatment in where you just fit a linear line to this different systematics and then upweight your galaxies accordingly. And in orange, you can see that this works well for intermediate range, but really fails at the edges in most cases. So you can see here is that you still get remaining systematics in your sample. Whereas with a neural network treatment, we can really account for all the systematics for the entire range that we see in our sample. Now here, for example, you can see what the results that I showed you earlier would look like if we had just used the standard catalog. that was used for the baryon RSD. And you can see that does not look that great. So on the left again for P of 1.6 and on the right for P of 1, where P of 1 means no recent mergers. Not only is there really a jump between the optimal weights and the non-optimal weights, but you can also see that the likelihood isn't really Gaussian. We're getting a double peak here in that case, and that really nothing makes sense. So you can also just see from here these two different measurements that there's clearly something wrong, and that there's some remaining systematics. All right, so now that obviously prompted us to do a lot of robustness tests, again on the left for the neural networks and on the right for the linear, so for the standard treatment, where we just, we varied the maximum K range, we varied the minimum K range, and a variety and different things, where you can see that with the neural network, we get really good consistency for all these different robustness tests we made. Whereas with the linear systematics, you see much more of a jump between the various measurements. All right, so now here is a summary. So this, the last data point is from my recent paper. So studying the eBOSS quasar sample, and you can see how, well, first of all, how from the CMB, the constraints still are tighter than what we get from large scale structure, but also how the Planck 2018 is the last data point where we really expect here much improvement from the CMB. And from the large scale structure side, how much we improve from just BOSS DR9 to using the eBOSS quasar sample and DR16, and then my study, sorry, DR14, and then my study with DR16. All right, but that's not it. I think I've mentioned it a couple of times. So now I had a slide that always said future surveys, the dark energy spectroscopic instrument, but we actually started taking data. So this is now a current measurement, and it's just a slide with which I want to end my talk, just showing you here the BOSS measurement of the Hubble parameter. And now with the DESI starting, how much tighter constraints we're gonna get over entire Redshift range. And I'd like to thank everybody and see if you have any questions.
Yep. Okay, thank you, Eva, for this very interesting talk. Thank you very much. So any questions from the audience? Please feel free to ask directly.
Hi, Eva. Thank you very much for the talk. It was very nice. I would like you to talk about a bit more about this merger parameter. Are you talking about an accretion of mass that is larger than a certain limit or something like that?
So this basically goes back. Let's see if I have the citation here. It goes back to a paper by Andres Loza, which was based on simulations. So I think it is from 2009. So I would refer you, or 2012, I would refer you to that paper with the details. As far as for me, for the study of the primordial non-Gaussianity, the important part is that the change in galaxy bias depends on this parameter. And also that if you were to marginalize over it, that the constraints would completely go away. So you have to have assumptions about that.
Thanks.
Okay, any more questions? I see Santi raised his hand.
I have a question.
Oh.
Eva, thanks for the talk. So you show this combining of BBN with the CMB data to try to fix the Hubble constant or R sub D.
Yes.
And my question is about how well we know BBN. In particular, there's been there's a statement that I don't understand very well that BBN is depends very sensitively to the neutron lifetime. And there's been ongoing problems determining precisely the neutron lifetime. So my question was, how sensitive is this to that? How well do we know BBN to really nail down the Hubble constant from this?
Well, so first of all, I should say, if you're not a big fan of BBN, you can also get similar constraints on the baryon density from the CMB. And if you were, and that agreement actually is quite well. So the BBN constraints on the baryon density and the constraints from the CMB and the BBN agree quite well when it comes to the baryon density. So it's really interchangeable which one you want to use here. As far as the details goes, I mean, I'm not an expert of Big Bang nuclear synthesis. But all the recent studies that I have seen at least confirmed the same measurement.
Can I comment here? Hi, Ben, and thank you, Eva. That was a beautiful talk. Actually, the neutron lifetime is not relevant here because most of the constraints from BBN on the baryon abundance comes from deuterium, not from helium. And this quantity is not so sensitive to the neutron lifetime. So typically you have your rates of reactions from helium to deuterium and from deuterium into the higher elements. And that's the critical part of the deuterium abundance. And that's what sets the omega baryon H square. So you're not sensitive to this uncertainty that I agree with you, it still exists in the neutron lifetime.
Thanks, Juan.
You're welcome.
Okay, any more questions? Something?
Yeah, I mean, it was a comment on, well, discussion between Violeta and Eva about this P value for the scale-dependent bias. So I mean, what I've read and is that in general, it's very difficult to have a clear prediction. The first papers were saying this can be 1 or 1.6, but then there are papers saying many different values. But I think in the end, what is important is what you were saying, that if it's FNL different to 0, it doesn't matter which p-value is, as long as you can distinguish FNL 0 from non-zero. So, and yeah, I don't know if you have any comment on that. And then I have a question. Okay. Now, if you, I mean, yeah. So that was a comment on that. And then the question is, probably also Juan was commenting this, that did you have to use any integral constraint on the power spectrum, or it was negligible in this case? Like when you...
Yes, I don't think I have a slide on it because I thought it's too technical, but yes, integral constraint rate matters a lot, and also the radial integral constraints.
Also the radial one, okay.
Yes, I think it's definitely was in the range of plus minus 10, 5 to 10 where it changed. Yeah.
Okay, thanks. Yeah, a great talk.
Okay, any more questions, comments? Pierre, yes?
Yes, thanks for the talk. Very basic question to finish, maybe. So could you explain why SDSS targeted, well, those targets, the LRGs and the emission line galaxies? And is DESI going to have the same targets?
So, I mean, so one of the reasons is because we really want to target the entire redshift range, right? So having the LRGs at very high redshift, like Redshift-II is not going to be possible. And you also want to have enough of it, a high number densities, that you can do statistics with that. Now the tracers, so for DESI, it's going to be actually very similar in that sense, that we're going to have LRGs covering up to redshift of 1, and then we have the ELGs in the intermediate redshifts, which is going to be the main sample, in the sense that the highest number of objects observed going to be the ELGs. And then also we're going to have the quasars going to the higher redshift. So in a way, is everything that we can was targeted. Right, we want something that traces the underlying dark matter and needs to be well enough understood. But maybe someone, I mean, as I said, it's 20 years of SDSS, and for 20 years I was still in high school. So maybe someone else can comment how the evolution of targeting these specific traces was.
But so maybe, again, this is probably a very simple and naive question, but I was wondering why can't we just take any galaxy that we see and do the same work? Is it because the sample will not be homogeneous enough, because the bias depends on the nature of the galaxy? Is it something like that, or a combination of all these?
Yes, it is. So the targeting, there is an entire working group within this collaboration that is dedicated to tinkering with the targeting. But generally speaking, you want it to be homogeneous, and you also wanted to have like a distinct group of galaxies to target, right? It's not a photometric survey where you just take a picture and then you look at everything. You really need to specifically target the galaxies you want to take the spectra from. I don't know if Santi wanted to comment, or someone else on that topic.
Yeah, so I think the general idea is that you want some targets that you have a good chance before getting the spectra of knowing what they are and what redshift they have, and I think because you have the photometric survey before the spectroscopic one, so you already have information on several bands, and if with that information for certain types of galaxies, you are able to already guess with a high probability the type and the range of redshift. So I think that's the idea, that you can know beforehand that you're likely to get a good redshift in the range you want.
So it's because you have to choose, you choose to choose the ones that are the best candidates somehow. Is that okay? Right.
Can I add maybe that the change of LRGs to ELGs is because at certain point you cannot measure the redshift of LRGs if the spectra has shifted, and then there's not enough features in the spectra, so you cannot measure high redshift LRGs properly, fast enough. And then you move on to ELGs, because those ones you can do that. So you can, because they have a doublet in O2, and then you can measure very fast the redshift, and then you have an homogeneous covering a sample covering a very large volume.
Thanks, Violeta.
Also, that's the point that you mentioned before about bias. So all of these different galaxy types inhabit different types of halos, and therefore they have a different bias. So it's good for you to know that they are a homogeneous sample over big redshift range, so that you can then compute things like the primordial non-Gaussianities using their bias. It is important to know what kind of galaxy you're talking about. You cannot mix pairs with apples, right? Because you get the wrong value. And this you distinguish by bias.
Okay, any more questions, Lucas?
Yes, thank you for the talk. So changing topic, at the end you mentioned quickly DESI. So my question is about your method for finding primordial non-Gaussianities. Do you have an idea of how much do you expect to do better with DESI about this? And for example, have you tried to apply your technique to mock data from DESI?
So Fisher forecasts. Basically, we're hoping to get roughly the same as Planck, so ±5, combining the different samples. but yeah, Fisher matrices are Fisher matrices. I mean, it really is going to boil down to how confident are we about the systematic effects, or if there are some remnant systematics that we don't understand. So if purely based on the statistics, the answer would be ±5.
Okay, so it's the best case scenario, let's say.
Yeah.
Okay, thank you.
Can I make a question?
Yes.
So Eva, of course, if we get a number for FNL, which is very different from that that Planck has suggested. So imagine we get 20 ± 1, or maybe ±5. Then how could we interpret this? Could we argue that FNL is actually a quantity which is not constant over different scales, or are we going to claim that there's something wrong with the primordial spectrum? How would you address that issue?
Honestly, after what I've seen, my first impression would be there's something wrong with systematics, and neither I wouldn't jump to any conclusions about the theory. I would, you know what I actually would do? I would look in what do you get if you look at cross correlations between CMB and large scale structure. I think that was the first thing from an observational point of view that I would look at. But sorry, so you were basically under the assumptions that it's not systematics. What could it be, right? Can you repeat again what you said?
Right. So imagine that you get a value which is very different from the CMB, which covers, of course, only the very large scales. And somehow you're finding that there are non-Gaussian characters in the statistical distribution of galaxies on much smaller scales, say megaparsecs or tens of megaparsecs rather than gigaparsec scales. Would you conclude that our assumptions, the underlying assumptions of what we call FNL, has to be re-established? Somehow it cannot be a constant quantity?
I mean, you could have a running within this FNL parameter, right?
Right.
But I don't think it would give you such a big effect. I mean, I don't know. I would have to think about it when it comes to it. Sorry.
Right. No, CMB, of course, covers a few e-folds, but it doesn't cover that much to tell apart whether FNL is a constant over all the different scales that have been probed by the CMB.
Yeah.
Of course, with a galaxy clustering, we have much larger little r because we can do 3D correlations, right, compared to the 2D that you do in the CMB. So somehow one should be able to infer much more information from galaxies. But it might happen that there is a scale dependence of this quantity, that the assumption that FLN is constant, like in local non-Gaussianities, is not quite correct. And we have to enlarge our vision to encompass this. This is one of the outcomes that could come out of the analysis.
Definitely, yeah.
Yeah. I just was wondering whether you had some other perspective on it. But I agree with you, systematics will be the thing that we'll have to work out first to be sure we're not being fooled by it. Yep.
Okay, any more questions, comments from the audience?
Yeah, if I can ask, so this new data vector, the power spectrum, or systematic treatment, has it been released publicly, or? Yeah,
it's when you go, so it's just a new catalog with the weights that are different. If you go to Mehdi's paper, there, I think if you just go on the archive, there should be a link to the catalog. I think they are just on NERSC.
And then another quick question is, do you expect that this systematics could affect BAO and RSD measurements, or
no? So, I should have mentioned there was another paper. Trying to think, it was one of Heejong's grad student who specifically looked at that and looked at how it affects the BAO, and it's because the BAO is at much larger K, so at smaller scales, and it didn't have that much of an effect. You can see it in the power spectrum that I showed you, that the majority of the here. Sorry, okay, the BAO bump, you can't see that well here, but it's before that. So no, I don't think for BOSS or eBOSS, it doesn't have any effect on the BAO. For DESI, maybe. I have a gut feeling that for DESI we should do something better than fit a line to these plots, which effectively what was done, right, in the standard analysis.
And do you think, for example, for the ELGs, that there was so much complications with the systematics, do you think this could help?
For the eBOSS sample specifically?
Yeah. Or do you think it was something completely different?
I think he tried, but the problem is also if you have very bad signal to noise, then also the neural network didn't perform that well. Because there was just too much scatter. So I know he had he looked into it, but ultimately I don't think managed to solve either the problems that exist within the ELG sample.
Okay, thanks.
But I should say, whenever it comes to machine learning, I think I'm sometimes a bit skeptical, because I feel like if we understand the physics, we should try to understand the physics instead of throwing the machine learning black box at it. But I think specifically in the case of systematics and photometric systematics, where we just don't really have a good fundamental understanding, and it depends on your survey and your targeting and the instrument, et cetera, I think there is really, I think more studies should go into how we can use machine learning to address that. Because I think it's really, for any kind of FNL, the most important thing is going to be in the systematics.
Okay, any more questions? Well, if not, then we can thank Eva again. Thank you again for this very nice talk. It was our pleasure.
Thanks for having me.